Welcome back everyone. Today's video is an explanation of problem F from the AtCoder Beginner Contest 307. I have provided the correct code in the video description, so please check it out after listening to my explanation. Let's begin with the problem statement. We are given a weighted graph with n vertices and m edges. The vertices represent people, and the edges represent the distances between them. On day 0, k people among them get infected with the virus, and their indices are listed in array A. The virus has an impact for d days, and the intensity of the impact varies each day, with the values given in array X. To illustrate this, consider the following example. On day 0, person 0 and person 8 get infected. On day 1, with an impact value of x1 equals 7, persons 1, 2, and 4 get infected because they are within a distance of 7 from either person 0 or person 8. On day 2, with an impact value of x2 equals 5, person 3 gets infected. Finally, on day 3, everyone expects person 6 gets infected. Our goal is to determine the day when each person gets infected. So the answer for this example is as follows. Let's proceed to solving the problem. Our initial approach is to apply Dijkstra's algorithm d times. We start with Dijkstra from day 0 to day 1 to determine the situation at the beginning of day 2. Let's briefly review how Dijkstra's algorithm works. We maintain a queue of already infected people and store tuples containing the distance from the infectors and the vertex being considered. We repeatedly select the tuple with the minimum distance from the queue, examine its adjacent vertices, and add them to the queue if they have not been reached before. This process continues until the queue is empty. In this problem, we can stop the process before the queue becomes empty since there is a limit on the distance, which is 7 in this example. The newly reached vertices during the process represent the new infectors from day 0 to day 1, so their answer is 1. Next, we perform Dijkstra from day 1 to day 2 using the information obtained previously. We already know the infectors up to day 1, which are 0, 1, 2, 4, and 8. We initialize the queue with these infectors and a distance of 0. We then apply Dijkstra's algorithm again. The vertices that are newly reached before the process ends represent the infectors on day 2, so their answer is 2. We continue this process for the subsequent days until we reach day D, where D is the number of days the virus has an impact. This completes the algorithm for the first approach to solve the problem. Unfortunately, the execution time exceeds the limit. Since the graph size can be up to 10 to the 5th, each Dijkstra operation takes 10 to the 6th. Considering that we repeat it at most 10 to the 5th times, the total time complexity of the algorithm is about 10 to the 11th. Our initial approach has failed. In practice, we have two options from here. First, we can discard Dijkstra completely and try another algorithm. Second, we can attempt to improve Dijkstra's algorithm. Given that the problem involves distances on a weighted graph and our knowledge is limited to this Dijkstra's algorithm, it's better to pursue the second option. The question now is how to improve it, which is the most challenging part of the problem. My idea is as follows. The slide shows the process of Dijkstra from day 1 to day 2. I propose skipping the initial part of the process and starting with the halfway queue represented in red ink. As you can see from the calculations, this is a significant improvement if feasible. I mentioned starting Dijkstra from day 1 to day 2 with the red queue, but how can we achieve that? The answer lies in reusing the final queue obtained during the process from day 0 to day 1. Take a look at the left diagram, which depicts the end of the process from day 0 to day 1. The red arrows indicate where the contents of the final queue originated. These contents consist of leftover vertices adjacent to infectors on day 0 or day 1 due to the large distances involved. Clearly, the adjacent vertices on the left side are the primary candidates for infectors on day 2. Therefore, it is natural to start day 2 with the final queue, hence the suggestion to use the red queue as the initial queue from day 1 to day 2. However, there is a small problem. When comparing the final queue from 0 to 1 with the initial queue from 1 to 2, some distances are different. In the process from day 0 to day 1, the distance represents the distance from the nearest day 0 infector, which is 0 and 8 in the example. However, in the process from day 1 to day 2, the distance should reflect the distance from the nearest infector between day 0 and day 1, which is 0, 1, 2, 4, and 8. To adjust the distances, we simply replace them with the weight of the last passed edge, since the last passed vertex must be an infector. Thus, we obtain a better initial queue based on the final queue. To connect the final queue from 0 to 1 with the initial queue from 1 to 2, we need to remember the weight of the last edge on the route. Therefore, we make a slight modification to Dijkstra from day 0 to day 1. Our approach involves using two queues named queue and new queue instead of just one queue. We place the already infected vertices in the regular queue and the newly infected vertices in the new queue. To retain the weight of the last passed edge, we store a tuple containing the distance, the vertex, and the weight in the new queue. The rest of the algorithm remains the same as the Dijkstra, but we must carefully choose the tuple with the minimum distance between the two queues. This means selecting the tuple with the minimum distance from each queue and then choosing the one with the smaller distance. If you are having trouble understanding, please follow the example and the corresponding calculations. Dijkstra from day 0 to day 1 is now complete, and we need to update the distances in the new queue. We create a mapping from the new queue to the regular queue where a tuple of distance t, vertex v, and weight w maps to a tuple of weight and vertex. Then we transfer all the elements in the new queue to the regular queue, emptying the new queue in the process. Now we are ready to start Dijkstra from day 1 to day 2. This covers the algorithm details. Finally, we need to assess the overall time complexity of the algorithm. Throughout the process, we employ a single Dijkstra operation. The addition we make to the regular Dijkstra involves the new queue, and we initially add each new vertex to the new queue before transferring it to the regular queue. The number of elements added to the new queue is equal to the number of edges m. Thus, it is akin to performing Dijkstra twice. We have successfully solved this problem, and I have completed the explanation. If you have any questions regarding the problem or requests to solve other ABC problems, please feel free to comment. Thanks for watching the video.